Okay, so we're going to look at, we're going to do the last unit of exponential growth, or the applications. Now, we already did like population growth, so we saw this with the formula. So the aim is population growth. We saw this with the formula, A equals P 1 plus or minus R to the T, and we come it over to K. And then once again, this is not money, so there's no compounding. But in general, we know this is the initial, this is the final. The formulas are always the same. This is the rate. So if the population is increasing, it's like 1 point something. If it's decreasing, it's like 0.87 or 0.72. We saw here, this is the time. And we saw this K down here. This was like the period when like growth happens. So for example, if I say in general, growth happens like, every year. But sometimes they'll say it happens every 30 seconds, or it like a half-life is 15 years. That's what the K is. So it's the growth, it's the rate period. And you'll notice that when they should say like every year, every minute. If they don't say one of something, that goes to the denominator. Okay, and so we have these problems, and a population of 500, giraffes grows at a rate of 15%. And so you knew, fine, y equals 500. It grows at a rate of 15%, and I would ask you for 7 years. And you plug it in the calculator. Or maybe I would say something like, the final amount was 1,000, it started at 700, and it grew at a rate of, 7%. How long did it take? Or, another example, I might say it doubled. And you'd be like, okay, fine, 2 to 1, and then this. Or I'd ask you to find the rate. Basic calculator problems. But the book, there's another example, and the idea is we're moving towards the probability and statistics chapter. The idea is that you've collected data, and so from the data, can we create these models? And that's what I want to concentrate on this lesson. So I photocopied the book, these examples, and so let's just take a look at them. So the first example is the population of Canada can be found in the table below. And what you notice is you're given some data. So, the year 2013, there was 35.152 million. In 2014, 35 million. 2015, 35.832. 2016, 36.264. And 2017, 36.708. So the first thing is, how do we model this? Well, we're told it's it's population growth, and we know population growth is not linear most of the time, but in this course it's going to be a rate. So the question is, how do we find the percentage growth? Well, what you're going to do is, how you would determine if something was geometric. So to find the rate, just take the quotient. Did I get a message? Yeah, just take the quotient. So in the same way that you would divide the next term over the previous term, you're going to do that here. So you're going to say 35.535 divided by 35.152. And what do we get? Why don't we figure that out in our calculators? We get, let's see, that is, I'm going to call it the first rate, and that's 1.01. So you might say, hey, Mr. Adler, let me see if that's constant. So you could say, okay, that's cool. So you're like, fine, let's take 2015. Let's take the number from 2015, 3, 2, and divide that by 35.535. Let's see if we get the same number. And we put it in our calculator, and it turns out we get something kind of close to it, 1.008. So you know what? I want to figure this out. How about we do the third one? We can do the third rate. We can say, you know what? I want to test this a little bit more. 36.264 divided by 35.832. I'm going to call this the third rate, and we get, let's see what my calculator says, 1.025. Now, it's kind of close to each other, but maybe I want to do one more. The last one is 36,705. 8 divided by 36.264, and I'm going to call this rate 4, and I get 1.012. Which one do I pick? Well, you have a calculator. Take the average. The average rate is, what do I got? 1.013. 1.013. And that's how you would find the rate. You would actually do that with data like from your biology class. This is how you would do that. So we found the growth rate between each year. We found the average rate, 1.013. What do they want? Create a general formula. Okay. U of t equals, well, we know from our growth unit, let's take the first one, 35.152. This is the initial value. We know that it's growing at a rate of like 1%, and that's over time. And so, next, last one, use your general formula to estimate the population of Canada in 2025. Well, we have to be careful. Can you see this? Yes, we have to be careful so we have to be careful. Remember, we started at 2013, so we started 2013, and then we're going to 2025. That's 12 years. So the population of 2025 is 35.152 times 1.013 to the 12th power. And you can figure that out in your calculator. We can do that. Let's see. Let's turn the calculator on. And what do I got? Let's see. 35.152 times 1.013 raised to the 12th power. I got 41,045. And so this is the idea of this unit. It's taking the data. So instead of writing rules down, let's just do these problems together, and let's just see what we got. So let's read the next problem. In 2015, let's see, example 26. In 2015, the population of Tokyo was 13.491. In 2016, we're told that 405,000 people moved in, but 331,000 people left. Question number 1, find the net increase. Well, 405 minus 331. You can take if you know it's a calculator problem, I would use the calculator. You know what? Nobody if it's a part 2 question, no one cares that you can do arithmetic. No one cares. So I'm using a calculator. I can do this. I'm not doing it. I'm using the calculator. Let's see. 405 minus 331 equals 74,000. So there's an increase of 74,000. Calculate the annual population growth rate. So what do you think? Well, so the growth rate let's see, what is 74,000 of? Well, no, I'm sorry. How do we figure out the growth rate? So we know that there was, so let's see. So therefore, in 2016, we had 13.491 plus 0.74. I'm getting out my calculator. So I have 13.491 plus 0, enter. So the new population is 13,565. I'm taking that number and dividing it by 13,491. Because remember, the second term divided by the first term. The population of 2016 divided by the population of 2015. And so let's take that number divided by 13.491, enter. It's about 1.00549. Now here's the great thing. Just write that down, leave that number in your calculator, raise that number to the power you need, multiply it by the initial amount, and then it'll take you to the final population. Let the calculator do the work. Don't worry about the decimals, but let the calculator do all this work for you. Good. Assuming the growth rate stays the same, find the general formula for the population. General formula. We know U of t is equal to, what was the initial value? 13.491 times the rate, 1.00549 raised to the t. And then they're asking for estimate the population of Tokyo in 2025. In 2025, you can see, okay, well, if we started in 2015 and went to 25, we know that t is 10. Stick that whole thing in the calculator. We have to write this down first. So, but I have this number in my calculator. So, I can take that answer, raise it to the 10th power, and then multiply that by 13.491, and I get an answer of 14.2495. 14.2495. Is that the answer? Yes. And then, is that the right answer? Yeah. 14.249. Yes. And then, sorry about that. So, and then they ask you why is it not accurate, and IB's not asking you that, but the book does say it doesn't account for births and deaths. Let's take a look at the next one, example 27. Let's take a look at the last problem. Same idea. A biologist is growing a culture of bacteria in a lab. She counts the number of bacteria in a dish every 6 hours. Right? So here are her results. Okay, fine. You're like 0, 6, 12, 18, 125 to 350. So you're like, okay, let me see what the rate. So create a general formula. You're like, no problem. There's a rate. I know what it's supposed to look like. Same idea. And once again, you're going to be doing, some of you might be doing this in your biology class. So you're like, okay, the first thing is the first rate is 350 divided by 125. Then you get your calculator, turn it on. 350 divided by 125. Sorry, I did 300. 350 divided by 125, and it's 2.8. You might be suspicious. You might say, Mr. Adler, I'd like to test the other numbers. Go for it. It turns out that 980 divided by 350 is also 2.8, and it turns out that 2744 divided by 980 is also 2.8, so we're in luck. So I'm going to do something a little different. Here. So we know the formula is, U of t is the initial amount, which is 125 times 2.8. The book says t, but you know what? I'm going to do the t divided by 6. Because I know every 6 hours, I'm only multiplying by 2.8. So if I put the 6 here, so for example, if t equals 6, I have 1.25 times 2.8, 6 divided by 6, which is simply the 125 times 2.8 to the first power. What the book says to do is figure out, how many periods is 6 hours. I'm like, no. Put the 6 down here, and then every the first 6 hours, it's 1. 12 hours, 2. 18 hours, 3. 24 hours, 4, etc., etc. And so, that's our formula. Good. Determine when the bacteria will determine your general formula to predict the number of bacteria at the end of the second day. So, at the end of the second day, we have 48 hours. But after 48 hours, how many compoundings? Or, let's use that word. So you say, okay, so after 48 hours, it's 125 times 2.8 times 48 divided by 6. And that's the idea of putting this number down here. That's the idea of that. Take your calculator out, turn it on. Let's see, what do we have? 125 times 2.8 raised to the 8th power, and we get 4. That's a lot of bacteria, right? 472,000, but that's exponential growth. 472,252. What's the next thing they ask us? They want to know when it exceeds 250,000. We did stuff like this. At what time does U of t greater than how many bacteria? 250,000. Well, you're going to put in first. You're going to write the equation down. 125 times 2.8 times whatever xt over 6 equals 250,000. And so you're going to do n solver. Open parentheses. You can just do times, comma, whatever variable you use, close parentheses, and you're going to get that answer. It should be the answer, and the answer should be 44.3 hours. If you got that number and it's 44.2, I'd be totally fine with it. Once again, this is a calculator question. And then the last thing, will the bacteria continue to multiply indefinitely? Explain your answer. No, because the book, overcrowding, that's not our problem. Anyway, work on the additional problems I gave you. Good. And then study for the test. So we're done with exponents. I want to test on this. Good.